Let's try again. Oh man. Oh, today's a tough day, huh? Okay, so keep going here. Let's check that the stream is working. Okay, so looks like it's working here. All right, so I'm just going to continue. Let me change the name of the stream. It's gonna be that one. It's gonna be this one. So hard. I wanted to finish this question. Okay, there we go. Sorry about that. Yeah, my stream keeps like dying here. Let me go ahead and continue. All right. So, just want to update the stream title. A runtime error. So I'm not sure if I explained the solution. Passing 0 to CLC. Okay. Oh, interesting. Oh yeah, there's an edge case I forgot. So let me explain how this works. Okay. This is actually also an edge case. If sig removed 0, return single bit something or other sig bit index. It's gonna be flip single bit, that's the one. Okay, flip single bit. So that should handle that case, I think. Just make sure. No. Oh, explain what's going on here in a moment. Oh, it works. Wow. Hey, I think I got it. Oh, that's awesome. I'm gonna go for it. That's very encouraging. Oh, I got it. Oh, I'm the best. 0 milliseconds, 100%. Oh, that's a good feeling, man. There you go. How you like that? How you like that? That's awesome. That's freaking awesome. All right, how's the, it's a lot of buffering. Okay. Oh, that's cool, man. That's so cool. That's so freaking awesome. Let me show what happened here. So I wonder if I could do this without all of these bits. Let me try this. I'll explain. Yeah, I think. And I'm gonna submit this one. See if it still works. I think it still works. Yeah. Okay. Let me do ints here. I still have to explain what's going on, but I think yeah. So these don't need to be longs. It's just the way this is computed. It's a little awkward. So as it turns out, I don't actually want to use that extra bit and calculate that for that extra bit because it makes things very awkward overall. All right, so very interesting, but this is a little redundant. This flip single bit and move bit to index, they're actually equal. Uh, they're actually equal numbers. Right? This calculation is the same, so I don't even need this part, this calculation. And this move bit to index and shift bit right is also equal. They only differ by 1. So I really only need to calculate one thing here. I don't know what to call it, but there's only one thing that actually needs to be calculated here, pre-calculated. Although I like to use these different names because it's easier for me to think about. So to explain what's going on here, I've got this couple of recursive base cases, another base case which I'll explain momentarily. This routine here, and then a recursion. A lot of interesting bit manipulation going on here, but it's basically a bit DP with some recursion. And this is tail recursive, so this could be iteratively. It doesn't have to be recursion, but it's a little bit easier to think about as a recursion. Okay, so let me submit it again. That's awesome. It's awesome that it works. So cool. So what's going on here is I do a pre-computation to figure out there's a move bit to index, a shift bit right, and a flip single bit. What this is going to do is the move bit to index is going to figure out how many operations I need to flip from a 0 to a 1 and then move that bit over to a certain index, given an input index. The shift bit right takes the bit at that index and shifts it 1 over to the right, just one over. The flip single bit is going to flip that bit to a 0. It's going to shift the bit to the right all the way until it's gone, basically. Now, in order to do these things, the move bit to index as well as flip single bit are actually equal, because the way it works is the move bit to index is going to move the bit to the previous index, which we calculate by induction. That's the inductive hypothesis. By induction, we calculate that. And then we're going to flip the bit that we're interested in, which we can do in one operation. So that's the 1 there. And then we're gonna flip the bit that we had just moved over. So we move a bit over, flip a bit, and then move that bit back, basically. And flipping a single bit is the same thing. We would move a bit over, flip the bit to 0, and move back. So both of these actually are the same, more or less. Moving a bit to a specific index and flipping a bit at that index from a 1 to a 0, 0 to 1, it costs the same amount. Shifting the bit to the right is very similar. We would move the bit to the index just before, and then we would add 1 to flip the bit that we wanted to move. So these are all very similar to each other. And in fact, this is the same as this, and these are exactly the same. I only need one of them. And then this one is only one more than this. So this is actually just this one, previous value plus 1. Shift bit to the right is just move index minus 1 plus 1. And then the move bit to index is equal to flip single bit. So I only need to calculate one thing there. And then the way that we actually we use this flip single bit to compute the result, which is the same, as I said, the same thing as move bit to index, is we're going to take a look at their number, take a look at the most significant bit, which we use a built-in to figure that out quite efficiently. Then we're going to flip that bit there to get the next most significant bit here. By the way, there is no most significant bit to flip. So basically, if once we flip the bit and it's a 0, then we can just return the amount to flip that single bit. That's something of an edge case. So we find out, so assuming we don't just have one bit to consider, if we have at least 2 bits, then we flip the first bit to get the index of the second bit. We get the 2 indices. And then what we do is we say, okay, we're going to recursively remove the, we're going to then remove the significant bit again, the next significant bit again. So now we don't have those 2 bits, they're removed. Recursively set that to 0 and calculate how much that takes. And then we're going to add to our total what it takes to handle these last 2 bits. So assuming we've already eliminated all the other bits, we want to deal with these last 2 bits. What we're going to do is shift the bit, the penultimate bit, we're going to shift it over to the most significant bit, and then flip the most significant bit, and then flip the what's left over. So it's going to be another single bit flip. In order to do this, all that's required is we use one operation to flip the bit to the left, and another operation to perform the single bit flip of the bit that we just operated on. So we have a bit, we flip the one to the left of it, and then remove the single bit, and that basically shifts it to the left. So we just perform that repeatedly, and as it turns out, we can do that. It's the same calculation for the last bit too, even though we're not going to flip to a 1, we're going to flip to a 0 and then remove the last bit. So we just perform that repeatedly. Add that all together, the total, add that to the recursion, and it should be a logarithmic, I think it's like log squared number of operations, but this could be optimized again to make it logarithmic. But there are only like 32 bits or so to work with, so making it like 900 bits, 900 operations or whatever instead of 30 is still extremely fast. So that's still going to give you 0 milliseconds regardless. Happens extremely quickly. I optimized this slightly by pre-computing in a immediately invoked lambda expression to get the move bit to index values, or get these 3 different values. But again, you only actually even use one of these anyway in the calculation, and this one happens to be equal to this one. And this one is not, this isn't even used actually. Yeah, this shift bit right is not even used at all, and is totally unnecessary. So there's an optimized code is just get rid of the shift bit right. We don't need it. Don't even use it. Flip single bit's the only one that we care about, which is they're equal to each other. So it's flip single bit twice, which is why there is a slight restriction in terms of making these things ints. This is not a prefix sum, by the way. The reason why this was overflowing is because it's slightly more than 2 raised to the whatever bit position it is. It's not exactly it's basically it's a recursion that is very close to like just flipping all those bits to 1, or very, very close to the powers of 2, I should say. It's very close to the powers of 2. It's not exactly the powers of 2. Yeah, I think this is still correct. That's why you don't want to go through all the way through 31 bits or 32 bits or whatever it was. It's still correct. That's cool, man. So optimized solution doesn't require as much memory. Yep. Pretty good. Pretty good. By the way, you could probably compute what this is and even compute this on the fly as a function instead of because it says I'm not using I'm using a slightly more memory than everyone else. You could probably compute this on the fly. The oh, this is not a lot of memory. 32 bits. It's not a lot. 32 integers rather. So yeah, pretty interesting question. Ended up being a very simple calculation recursion. Really cool question. This was hard. Yeah, this took a while, man. This took me a long time. This took me time. What's up, chat? Okay, yeah. So that's my solution to this one. Let me read the question again so folks have an idea what's going on here, and then I'll explain why this works. But yeah, that's why I couldn't use the long. I had to use the int. So 1611, minimum 1-bit operations to make integer 0, given integer n. Must transform it into 0 using the following operations any number of times. Change the rightmost 0th bit in the binary representation of n. Change the ith bit in the binary representation of n if the I minus 1th bit is set to 1 and all the other bits to the right of it, the I minus 2 through 0th bits are set to 0. Return the minimum number of operations to transform n into 0. So I went with a DP recursion approach. And I basically noted the core operation is going to be taking a bit, shifting it, flipping it from a 0 to a 1, shifting it down to the left a certain number of indices, certain number of operations, and then either flipping the bit to the left of that to a 0, from a 0 to a 1, or from a 1 to a 0. Yeah. And the way I expressed this was as flip a single bit. So what would happen is if you do, let's say you move it to the right and then flip that bit right, and then you move this back, it would be, if it's the same operation to flip a bit, like the same cost to flip the bit is going to be equivalent to, how does it work? So it was basically, I figured, okay, so I guess the right way to think about this is the cost to flip a single, so move 1 over to flip a single bit. And if you could go from, if it could be flipping it from 0 to 1 or 1 to 0, rather than just moving the bit over, flip it from 1 to 0, then in order to flip a particular bit, the next one, I'd flip this bit to a 1 operation to flip the next bit, and then the same amount to flip that bit again. So as it turns out, I could express this much more succinctly by saying just flip a particular bit, and then in order to flip the next bit, I'm going to flip this bit from a 0 to a 1, flip the next bit to whatever it's supposed to be, and then flip the bit that so I guess there's bit 1 and bit 2. I'm going to flip bit 1, which I've already figured out the cost to flip bit 1 to 1. Then I can flip bit 2 to whatever I want, either 0 or 1. And then I can flip bit 1 back to 0. And this is assuming, by the way, that all the values from right to left up to that point are zeros. So that's this pre-computation. So as it turns out, this calculation can be made much easier if I just calculate this subroutine and pre-compute it. And again, it's very easy to figure out because it's just going to be 2-bit flips of the previous bit plus the 1 operation to flip the bit that you're interested in, which is so it's a very simple recursion, or recurrence relation. And then for the base case, I just say if there's 2 or 1, I would return 0 if it's 0, 1 if it's 1, and then 3 if it's 2. And the reason I did this is that I basically wanted to exclude the first 2 bits from these calculations because it gets it was just really confusing for me in terms of like how to think about it, like whether or not there would be issues because you have access to the first bit, but you don't have access to the other bits easily. So I reduced it to flipping a single bit, and then I said, okay, you can do it recursively by saying, take the most significant bit, take the next most significant bit, and what you're going to do is you're going to first to remove those two and recurse on what's left and turn those all to zeros. Now you can work with those 2 bits kind of unimpeded. If there aren't 2 bits, there's only 1 bit in the whole thing, then this is obviously just the operation to flip that single bit. So we do that. But if there are at least 2 bits left over, so that's, by the way, here's the recursive part. So I removed those 2 significant bits. And again, you can use CLZ to get the most significant bits. That's this part. Built-in CLZ. So in order to move the penultimate bit over, so that way we can flip the most significant bit, we're going to perform a single operation for the bit to the left, and then bit flip the one we started with. So we're going to keep kind of moving over that way. And as it turns out, the same operation works for when we want to flip the 1 to a 0, which is the most significant bit. So we don't have to like change operations or anything. We can just keep doing bit flips at the index from right to left, and then also include flipping the 0 to the left to a 1 each time. And then at the end, instead of flipping it from a 0 to 1, it flips to a 1 to a 0. So that's the summation. And again, this could actually be made as a prefix sum to do this in constant time rather than a logarithmic time. So technically the recursion right now is it's log squared time, not logarithmic, but this could be easily optimized. So yeah, that's the whole solution. A lot of stuff involved, pretty tough for me to figure all that out, quite frankly. I even had an issue where I didn't realize that it was going to overflow if I calculated a certain way. This is just server variance, why it's giving me 2 milliseconds instead of 0. Oh yeah, I also use thread local because this computation is going to be thread local and immediately invoked lambda expression, because this is going to be reused for every question. It's going to be the same, a single bit calculation. Yeah, it was a lot of stuff involved there. It was hard for me to think it all the way through. I used a bunch of different operations. Like if you look at my notes here, I have a few different operations. I didn't make it as simple as just use a bit flip calculation, and that makes the whole thing a lot easier to think about and to use. Yeah, this is tail recursive, so this could be made iteratively as well. It could be iterative and it could be logarithmic, linear in the bits, by just optimizing this part out. But I think it's a little easier to think about to do it recursively, quite frankly. I think it's kind of confusing to try to do to optimize this tail recursion. Is not so obvious what to do. But I guess it's not the worst thing. So yeah, pretty good overall. Thank you all for watching. Do appreciate it. I'm probably going to take a break. I think I just wanted to finish that question because I was working on it for a bit there. If you like the stream, don't forget to give it a like. If you like the kind of stuff I do, give me a sub so you can subscribe to, so you see me when I'm doing things. If you don't subscribe, very likely that you're not going to see me doing stuff. I don't know. I mean, YouTube pushes things out, but it's a little bit doesn't always get out there, I guess. But yeah, let me stop here. It's been a few hours that I'm programming today. I want to take a break, and then I'll probably come back and do another 4 hours. But yeah, thanks again for watching. Take care. Talk to you soon. And yeah, that's my solution to number 1611 here. It's pretty good. That was a hard question. That was a good one. That was a hard one. I'm just glad I was able to figure it out. I'm a little bit better at the kind of number theoretic stuff.